Hello everyone, so for this video we're going to talk about finding zeros of polynomial function whose leading coefficient is greater than 1. And for our learning target in this video, hopefully after watching this video, I hope you can find the rational zeros of a polynomial function using rational zero theorem. Okay, so let us have here our problem. Find the zeros of the given polynomial function. Of course, to start our solution, let's make use of the rational zero theorem wherein we just simply get the ratio of the constant and then the leading coefficient. So we have P over Q. So by the way, what do we mean by P? P, it refers to our constant, which is negative 12, and our Q, which is positive 2. Okay, positive 2, so it came from our leading term, which is 2x cubed, so we have here 2. And of course, this is not yet the final process for us to find out the possible zeros that we may use for our trial and error in synthetic division afterwards. So we still need to get all or list down all the factors of our P and Q. So I just would like you to focus on what are the factors of 12 and what are the factors of 2. So first we have here in our numerator, what are the factors of 12? So we have positive and negative 1. What else? Positive and negative 2. What else? Positive and negative 3. We can have as well positive and negative 4. We can have positive and negative 6 and positive and negative 12. So I guess we're done. So for those who want to check, how would you know that a particular number is a factor of the given number? You just simply do this. For example, 12 divided by 1, so there's no remainder. 12 divided by 2, there is no remainder as well. 12 divided by 3, there is no remainder as well. 12 divided by 4, and there's no remainder as well, and so on. So if there's no remainder, automatically you may conclude that that particular number is a factor of the given number. Next, what are the factors of 2? So of course we have positive negative 1 and positive negative 2. Okay, so in our previous lesson, if the leading coefficient is just 1, and that means the possible zeros would be identical to the factors of the constant term. That is based on our corollary concept to rational zero theorem, which we use also on our previous lesson. So that means we can now conclude that our possible zeros are, so of course 1 divided by 1 we will have positive 1, or negative 1 divided by negative 1, so we will have positive negative 1. So for now we will just focus first with the first set of the factor of Q, which is positive and negative 1. For a while you are supposed to disregard first the positive and negative 2 so that you will not be confused. Okay, next, positive and negative 2 divided by positive and negative 1, we can have positive negative 2. And positive negative 3 divided by positive negative 1, so positive and negative 3, and so on. You just simply copy all the factors of P. Okay, and next to that, we're done. So positive negative 12 divided by positive negative 1, we will have positive or else negative 12. And now, would like you to focus already with the second set of the factors of q, which is positive and negative 2. Now let's simplify this. Positive and negative 1 divided by positive and negative 2. Do you think we can still simplify if this is the ratio? So actually no anymore. Therefore we can say that we can also have positive and negative 1/2 as one of the zeros of the given polynomial function, maybe. And next we have, how about positive and negative 2 divided by positive and negative 2? We can still simplify this, right? This is equivalent to either positive 1 or negative 1. And as you can see here in our possible zeros, we do have positive and negative 1 here already, and there's no need for us to duplicate this one. So moving on, positive and negative 3 divided by 2, we cannot simplify this further. Therefore, next possible zeros would be positive and negative 3/2. Okay. Moving on, so for our positive and negative 4 divided by positive and negative 2, we can still simplify this, and that would be positive or negative 2. And again, we cannot duplicate the positive and negative 2 anymore. And same goes with positive and negative 6 divided by positive and negative 2. We can have positive and negative 3. And positive and negative 12 divided by positive and negative 2, it will be simplified to positive or negative 6, and therefore we cannot duplicate as well this set of zeros. So finally, these are all the possible zeros of the given polynomial function. Now if I will be asking you how many possible zeros all in all, based on the given polynomial function, you just simply count 1, 2, 3, 4, 6, 12, 1/2, and 3/2. So we do have 8 values here, but we do have positive and negative. So you just simply multiply it to 2. So 8 times 2, we do have 16 possible zeros. So out of this 16 possible zeros, we are expecting only how many zeros? How many zeros? We are expecting 3 zeros only, because here in our degree of polynomial function, it's cubic or 3. Therefore, we will have 3 real zeros coming from the 16 possible zeros that we have got from the rational zero theorem that we applied. So here, of course, for us to determine the 3 real zeros of the given polynomial function, just simply use our trial and error technique involving synthetic division. So out of this 1, 2, 3, out of the 16 possible zeros, let me try positive 2. Okay, and we are going to list down all the coefficients of the given polynomial function, and of course we really need to check first if the given polynomial function is already arranged in decreasing order. At the same time, it has a complete pattern. As you can see, we do have here cube, squared, then we have first exponent, and then constant. So it's complete. So we can now directly list down, starting from the leading coefficient, which is positive 2. Next to that is positive 3. Next is negative 8, and next is negative 12. Okay, and then continue the process of the synthetic division by first we are going to bring down the leading coefficient, which is 2. Then 2 times 2 we have 4. 3 plus 4 we have 7. 7 times 2 we have 14. Negative 8 plus 14, we will have positive 6. 6 times 2, we will have 12. Oh, we got this. remainder, which is 0. So therefore, we can say that positive 2 is one of the zeros that we are looking for. Next is, let's say I'm gonna use negative 2. Okay, I'm gonna use negative 2. So, and for the leading coefficients, it is better for us to use the coefficients coming from the first synthetic division that we've done. So, 2, 7, and 6. But anyway, if you want to use the original coefficients coming from the given polynomial function, it's still okay because you will arrive with the same answer. But better if you use this one, the simpler form, because it is easier for you to do the synthetic division because of the coefficient which is in lower value already. So 2, bring down 2 times negative 2 will have negative 4. Then 7 plus negative 4 will have positive 3. 3 times negative 2 will have negative 6. And there we go. We got a 0 remainder as well. Therefore, we can say that negative 2 is also one of the factors, one of the zeros of the given polynomial function. And if you can still remember, out of the given polynomial function based on the degree, we are just looking for 3 zeros, real zeros. So we do have positive and negative 2 already. And for us to find out the remaining 0, so we can use this leading coefficients that we got here in our second synthetic division that we did. So here 3 is our constant, and then for our linear term, so we have 2x plus 3. And of course, for us to get the value of x here, for our third 0, so just simply equate it to 0. So this is our depressed equation already. And of course, apply the necessary properties. So that is addition property of equality. So I know you are more particular with the shortcut, which is the transposition. So I'll just transpose positive 3 will become negative 3. And apply again multiplication property of equality. So here, and also you are more particular with the shortcut by simply dividing both sides of the equation. So you will have x is equal to negative 3 halves. Therefore, we can conclude that the third 0 that we are looking for is negative 3 halves. And we're done. So finally, our final answer, the zeros of the polynomial function given are positive 2, negative 2, and negative 3 halves. So that's it for this video. Thank you so much for watching. I hope you learned about finding the zeros of polynomial function whose leading coefficient is greater than 1. Thank you.